So I was letting my mind wander the other day, and I started thinking about the Collatz conjecture, as one does. And for those who do not know, it is the easiest problem that we know of, or at least it is hailed to be the easiest problem that we know of, that is both unsolved and incredibly easy to state. And it goes as follows. So we have an input, and if that input is even, then we divide it by 2, but otherwise we multiply it by 3 and add 1. And then we take the output of that function and we feed it back into the input. And the hypothesis, the conjecture here, is that for all positive whole numbers, the input, once you feed it through that function some number of times, is eventually going to go and result in the sequence 4, 2, 1, 4, 2, 1, 4, 2, 1, so on and so forth. And you can see here that if we put in 4, we're going to get this branch here, so we're going to divide it by 2 because 4 is even. And then we're back to here, we have 2, which is even, so we're going to divide it by 2. And then we have 1, which is odd, so we're going to multiply it by 3 and add 1, which is 4. So we get back to that start, so which is why we get 4, 2, 1, 4, 2, 1. So my question is, what numbers can we put into this Collatz function which go only through that 3x plus 1 branch? So they go up very big, and then they go only through the division by 2 branch, so they go all the way down. Hello, my name is Sawyer West, and today we're going to be talking about clean Collatz branches. I'll be using C++ 20 and Visual Studio 2022 for coding today. I won't be getting too into the weeds with the coding. I'll be talking just about the meat of what's going on here, and then I will be going and showing the results. By meat, I am going to be looking just at this Collatz step and the Collatz sequence, and maybe the main function. As you can see, it's a little bit more general than earlier, but we have a divisor, which that is going to be 2, a scalar, which is going to be 3, and the addend, which is going to be 1, and then we have our input x. All of these are const, which means they're not going to change throughout, except this down here, which we will see why that is not const later. And these are all going to be uint64t's, which means it is a unsigned integer that we represent with 64 bits in binary, because we might want to represent fairly large numbers. This no discard here is a tag that allows the compiler, if it sees this function called and we don't store the input, that's going to give a warning to me. And that is foolproofing my code against my own stupidity. So we have 2 functions here, this Collatz step and this Collatz sequence. Inputs are largely the same as explained earlier. This one just outputs an individual step in the sequence, and this one outputs the entire sequence. So we're looking at the Collatz step right now. We're taking in this x input, and we're checking if it is divisible by saying, hey, if you divide it, does its remainder equal 0? And if so, it is divisible, so we're taking the input and we're dividing it by the divisor and we're returning that. Otherwise, we're going to go through that 3x plus 1 branch. However, we want to make sure our code doesn't crash. And if we're multiplying by 3 and adding 1, we could get large numbers quite quickly. So we're going to check what the largest number we can store is by using numerical limits. And we're going to perform the inverse of that 3x plus 1 step. So we're going to subtract off 1 and then divide by 3 here. And then we're going to check if that whole thing is smaller than our input. And if it is, then by performing that 3x plus 1 step, we're going to have an integer overflow. So the output is too large for us to represent with 64 bits. And that means we should probably throw a runtime error. Now, I have the comment here that this is unlikely to happen, which is true because that is a particularly large output. But it is not good practice to just stick these likely and unlikely tags on branches without testing if it makes it more or less efficient. And I really didn't want to go and do that, so I just left it as comment. But if we don't go and have integer overflow happen, then we're going to return the scalar times the input plus the addendum. Now, to return the entire sequence, we start off with this vector sequence, and we have the input stored in there already. And while the input is not equal to 1, we're going to set that input to the next step by running that aforementioned Collatz step function, which I just showed you here. And then we're going to push that input back onto the sequence. And then after we run through and find a input that is equal to 1, we're going to stop and then return the sequence, so we don't just get stuck in an infinite loop of 4, 2, 1. Our main function here wraps up those two inner functions inside of cout clean Collatz branches. So that's going to filter out anything that doesn't go and go all the way up through the 3x plus 1 branch and then go all the way down through the division by 2 branch. And then it's going to output that in a very clean way. So we're at a bit higher level of abstraction. It's some quality of life stuff here that I'm just not going to show you. But there's also some other stuff that I'm going to just hand wave here. We have this prime handler function, or object, that I have shown some ways of how it works in other videos, and I'm not going to show it here. I kind of encourage you to go and watch those if you're curious, but that just handles anything with prime numbers that I care about. But here we're going to say, okay, what's this lower bound of Collatz seeds that we're going to throw in, and what's the upper bound of the Collatz seeds that we're going to throw in? So we're going to start at 1, and then we're going to go all the way up to, what is that, 1e8, and 1e6 is a million, so that's 10 million, I think. Maybe. But it's some arbitrarily large number, and 1e9 didn't really work out that well because it was too large for my computer to handle. So we're going to have the inputs here, the scalar, addend, and the divisor declared, the 3x plus 1, and then the over 2 part. And then we're going to just feed all this into that wrapper function I mentioned earlier. And if the error that I mentioned, that overflow, happens, we're going to catch it and then display that to the user. And now we have the output. We can clearly see. And you don't have to just take my word that this is valid, although the first few, 1, 2, 4, and 5, 8, 16, those are pretty easy to verify by hand. After that, it gets a little bit frustrating, and possibly you need to pull out a calculator. So I also printed out the sequences that are outputted with these seeds. So take a moment if you want to try and find any patterns yourself before I point out one I found. And if that moment's over, we're going to continue on. So observe here that other than that first bit, that 1, any power of 2 is going to be in here. And every third element, right, so 5, 21, 85, that's not divisible by 2. But there's always 2 powers of 2 in between each of those non-divisible by 2 bits. And my hypothesis is that just keeps going on forever. And you can see here I showed it in this column format up to 2 to the power of 19, but we do see that it gets more results here. It goes up a bit more. With this prime factorization, you can very clearly see all these are just powers of 2, and these are not. So, one more thing I was curious about, because the number 2,731 and 8,191 doesn't really mean much to me. I decided to say, okay, what's the index of these prime factorizations that I'm getting out? So I took a look, and we are doing zero-based indexing, so the 0th prime is going to be 2, which is why you see all these zeros here. The first prime is going to be 3, the second prime is going to be 5, so on and so forth. And an interesting little pattern emerges. So we get a lot of these indices with greatest common divisors, at least for parts of it. So 14 here is divisible by 7, so it's 21, 56, and 63. So that's 7 times 2, 7 times 3, 7 times 8, and then 7 times 9. Here we see the sequence 1, 2, 3, and 6, which is interesting because you have the prime factorization of 6, the first perfect number, where the sum of its prime factorizations equals itself. We see that this number down here is divisible by this number up here. And stuff like that. It's quite interesting to look at. That's about all the results I pulled out of this little experiment. Thank you for watching. Please like, subscribe, remember to hit the bell. Thank you for watching.